Hey everyone, let's talk about investments and specifically portfolio theory and now portfolio choice. So we've learned about utility functions, we know how to apply them to the characteristics of any risk asset or portfolio, and we now know how to calculate the return and standard deviation of a portfolio, and indeed we learned how to combine a risky and a risk-free asset. But we still didn't really get into how we create that risky portfolio to begin with. So let's sort of bring everything together and figure out how we can create an optimal portfolio from the ground up, including our optimal allocation to individual risky assets, and then our optimal allocation to the risk-free asset and the risky portfolio. But first, let's review why we actually talk about portfolios. The basic idea why we actually will want to hold portfolios of assets rather than assets individually is due to the concept of diversification. In other words, there's some component of an asset's risk that is what we call systematic. That's the stuff that sort of earns this risk premium in a Sharpe ratio sense. But each asset also has some peculiar unsystematic or idiosyncratic risk that actually doesn't. You can think of it as like the risk of a scandal or a CEO departure or fire or supply chain disruption, any sort of unpredictable, firm-specific, unrelated to sort of the big market type of risk, we would call idiosyncratic risk. We don't expect that to carry a risk premium. And therefore, that just sort of introduces extra noise into our portfolio. But the good news about portfolios is if we hold a lot of assets in them, then this noise that's due to any individual position will essentially get smoothed out the more positions we hold. In other words, the risk of anything particularly bad happening to any particular firm is of course reduced if we hold many firms or many risk assets in our portfolio. And indeed, maybe they'll even be canceled out by something good happening to some other firm. So we can think of this, and we will think of this later on when we talk about risk factor models, in terms of a factor exposure that actually has its own factor-specific volatility, where then the riskiness of a portfolio is just your exposure to the factor times the risk of that factor, plus the overall idiosyncratic risk of the whole portfolio. And if we hold enough risk assets in the portfolio, we will observe a behavior similar to this, where the idiosyncratic risk of the whole portfolio will go lower and lower as each individual asset-specific perturbation will get smoothed out by the other asset-specific perturbations, and really only the market risk will remain. This is the stuff that you get the risk premium for. This is sort of the risk that you actually want to take, and we'll see how this relates to sort of the risk you would take on the capital market line or any capital allocation line when we talk about risk factor models. But for now, suffice it to say that diversification reduces your portfolio risk really just to what is priced. And indeed, it can reduce your portfolio risk substantially. Let's look at an example. So let's say that we've got a risky asset that we're going to represent as a payoff tree. It's got a 50-50 chance of ending up in one of two states. It starts with a price of 40, but it can go to 60 in an upstate if things go well, and down to 30 in a downstate if things go bad. Net payoffs then are 20 and minus 10, and the expected net payoff is, well, 50% chance of 20, 50% chance of minus 10. Net payoff is an expectation 5. Now, suppose we've got its mirror opposite, risk asset 2, which has the same initial price, but In the upstate, when things go well for asset 1, this one does actually badly. It loses 10. And in the downstate, when asset 1 loses 10, this one does well and gains 20. Then, of course, the expected net payoff to this one, since the payoffs are actually the same as those of asset 1, just flipped in their respective states, the expected net payoff is the same at $5. Now, you can probably see where this is going. What's going to happen if we combine these two risk assets? If you remember our example of the house and house insurance contract from modeling payoffs, the discussion we had prior to this one, you'll sort of already intuit what's going to happen. Well, let's actually go through it step by step. So let's say that we will hold a 50-50 portfolio of assets 1 and asset 2. And so what's going to happen? Well, the upstate still occurs with 50% probability, and now in this state we're going to get our weights, remember, are 50-50, so we're going to get 50% of the payoff of asset 1, 50% of the payoff of asset 2, and those, of course, will work out to a total payoff of $5. What about the downstate? That one occurs with 50% probability, and again, we have a portfolio that is 50-50 allocated to asset 1 and asset 2, so we have 50% of the payoff of asset 1, negative 10 this time, and 50% of the payoff of asset 2, 20 this time. And again, that works out to a net payoff of 5, and therefore the expected net payoff to this portfolio is also 5. No matter whether you're in the upstate or the downstate, the payoff is the same, it's $5. So we have actually created a risk-free asset by combining these two perfectly negatively correlated assets. And just as the house insurance contract was negatively correlated with the value of the house, particularly in the disaster state, so we observe this here, just an even more sort of exaggerated example. Now, in reality, of course, we're going to struggle to find two assets that are perfectly negatively correlated. Indeed, most assets are positively correlated. But that doesn't mean that diversification doesn't work. So let's look at this more generally. Let's say that we have two assets. We've got some weight on asset 1, some other weight on asset 2, but let's say that these are the only assets that are in our portfolio. Well, that means that really asset 1 and 2 add up to 1, and therefore the weight on asset 2 is really just 1 minus the weight on asset 1, which now being really the only weight that matters, we can denote as just W. We don't have to have these subscripts because, again, if we know the weight on asset 1, we will know the weight on asset 2 as well. And let's say that they have some covariance, so probably not perfectly negative, but it could be negative, it could be 0, it could be positive. And then, of course, that means that if we know the return and variance of each individual asset, and therefore we know their standard deviations, we can then also calculate the correlation between these two assets. So what weights would we have to actually hold to minimize the total risk in our portfolio? This is going to give us what we call the minimum variance portfolio, and when we talk more about factor models, we'll return back to this idea. But for now, let's just think about it from a pure diversification perspective, how we can reduce our total portfolio risk, in this case, down as low as it can possibly go. So this is where, again, knowing that formula for the variance of a two-asset portfolio can really get us a long way in terms of building intuition. And this is why I advocate that you do memorize it, not because you use it directly, but because you can refer to it to sort of help conceptualize more complex portfolio management problems. So if we do have these two risk assets, remember the variance of the portfolio will be just the weight on the first one squared times the variance of the first one, the weight on the second one squared, times the variance on the second one, times 2 times the product of the weights and a covariance between the two. And since we now know that really the weights on asset 1 and asset 2 are the same thing as the weight on the first one times 1 minus the weight on the second one, we can simplify it to this expression, also substituting in our definition of covariance as standard deviation of 1 times standard deviation of 2 times correlation. And we can, since we only really have two assets that we're dealing with, we can suppress the subscripts and just call this correlation rho, since we know it's the correlation between our two and only two assets. So now let's minimize this expression for variance using calculus. Can we do it? Well, we should be able to, because again, the only thing that we can really control is this weight on the first asset W. The rest of the parameters are given to us by the market. So let's think about what this would actually get us. Let's consider a special case first where the two assets are perfectly negatively correlated, as they were in our toy example with payoff trees. Then we can actually simplify our expression for portfolio variance. We're still going to have the variance of the first asset term, variance of the second asset term. We're going to substitute -1 for a covariance term. And that means that we can then, by collecting terms, say that the variance of the total portfolio is just the square of the weight on the first asset times the standard deviation on the first asset, minus 1 minus the weight on the first asset times the standard deviation on the second asset. And you can actually verify using algebra that if you distribute this exponent back into the parentheses, you will get this exact same expression. So essentially all we've done is just, with a bit of factoring, turned it into this exponentiated form. Now, if that's what it is, then we know that we can actually set this to 0 by simply setting the weight times the standard deviation of the first asset minus 1 minus the weight times the standard deviation of the second asset. If we can set the term inside the exponent equal to 0, of course then 0 to the second will also be 0. So actually we don't even need to do this part with calculus, but we could take the derivative with respect to W if we wanted to. For now, let's just say that we're going to minimize the term inside the exponents. That means that we just really solve for W. We can move the 1 minus W times the standard deviation of the second asset over to the right-hand side. We can distribute the standard deviation of the second asset into the 1 minus W, and then we can actually solve for W as the ratio of the standard deviation of the second asset over the standard deviation of the first plus the standard deviation of the second. So in the simple case where our standard deviation of the portfolio actually turns into this square form, we actually don't even need calculus. Now let's consider a more general case where the correlation is not -1, but can be anything else. And that means that we minimize now our expression for portfolio variance with these two risky assets with respect to our only decision variable, the weight on the first asset, which will then of course determine our second asset, which will then determine everything else given the variances and covariance between these two assets. So if we take the first derivative of this expression with respect to W, what do we get? Well, remember, we can do this term by term, so the derivative of this first term is just 2W sigma 1, which we see here. The derivative of the second term is, by the chain rule, 2 times 1 minus w, sigma 2 squared, which we see here. And we have that negative 1 because then we take the derivative of the minus w within that first function. And finally, the derivative of this component with respect to w, well, that's going to be the product rule. So we can say that that's going to be 2 times 1 minus w, or I guess 2 minus 2w, sigma 1, sigma 2p, plus minus 2w, sigma 1, sigma 2p. And if we collect terms in sigma 1, sigma 2p, or sorry, sigma 1, sigma 2 rho, that'll get us exactly this term here, 2 minus 4w, sigma 1, sigma 2 rho. And of course we want to set this to 0 to get our first order condition, to get a minimum or maximum. Now we can simplify this expression a bit by dividing both sides by 2. Remember, of course, we can divide the right-hand side 0 by just about anything, so long as it's not 0. So we can cancel this 2 and turn this 2 minus 4 into a 1 minus 2w. And we can distribute sigma 1, sigma 2 rho into the 1 minus 2w to get this expression. And now, really, all we need to do is collect terms in w, bring everything that doesn't have a w into it over to the right-hand side, and then just solve for w as the ratio of what we factored out that has the w in it, sigma 1 square, sigma 2 square, minus 2 sigma 1 sigma 2 rho, which we see here. And we just divide all the stuff that didn't have w in it by that. So this is our optimal expression, now derived using calculus, for the minimum variance. Now we can actually check that our fancy calculus solution is as good as our intuitive solution for the special case. How do we do that? Well, we just substitute in the correlation of -1 into our general case calculus-based formula. And if we do, then instead of minus sigma 1 sigma 2 rho, we get plus sigma 1 sigma 2. And if we factor out a sigma 2 from the top and bottom, we will get, or sorry, if we factor out a sigma 2 from the top and factor the bottom as essentially a product of two same terms, sigma 1 plus sigma 2, we can then cancel a sigma 1 plus sigma 2 from top and bottom, and indeed we can then recover that same expression that we had initially derived for the special case. So that suggests to us that this is indeed a sensible way to go. Now another thing that we can consider is what would happen if the assets were completely uncorrelated. We can again take our general calculus-based solution and substitute 0 in for the correlation. Now this is a often discussed property. For example, many hedge funds or alternative investment strategies will aim precisely for this, for uncorrelated series of returns. Very few people will promise negatively correlated returns, but uncorrelated is perhaps more often, and then the weight that we would assign to one asset that is uncorrelated with another, well, that whole minus sigma 1 sigma 2 rho term just disappears because rho is 0. And then this is our optimal weight. And finally, we can even figure out what our optimal weight would be if the assets were perfectly correlated. We can see that now we just substitute 1 for rho, so instead of minus sigma 1 sigma 2 rho, we just get minus sigma 1 sigma 2. We again complete the square at the bottom, or well, just perform the quadratic factorization at the bottom, factor out a sigma 2 at the top, and our ratio is sigma 2 over sigma 2 minus 1. Now does that make sense? Well, since we're trying to go for the lowest possible portfolio variance, let's actually plug in some numbers. Let's say that asset 1 has a standard deviation of 10%, asset 2 has a standard deviation of 20%, so the first asset is less risky. What would our optimal weight be if their correlation were 1? In other words, if there was no benefit to diversification. Well, what would be the weight on asset 1? The standard deviation of asset 2 is 20%, and the difference between their standard deviations is 10%. So the weight on asset 1 would actually be 2. Now you might wonder how you can get that. But of course, then the weight on asset 2 would have to be 1 minus that, or minus 1. So what this suggests is that essentially we're going to take a short position in the higher risk asset, and we're going to take a leveraged twofold position in our less risky asset. So it seems to make sense that this formula suggests that we will go all in on the risky asset, on the less risky asset, and actually short the more risky asset.